Okay, this lesson and probably the next one as well is going to cover another favorite topic of mine called optimization problems. As the name implies, it's basically using calculus to find optimal solutions to real world problems. Okay, so let's start with a very simple one, but it's kind of classic in showing what can be done. Suppose you've got a river, a nice straight river as it turns out, and you have a farmer with sheep, and this farmer wants to build some sort of a pen with fence that is three-sided and butts up against this river, so that for a couple of reasons. One is then the sheep can drink from the river, and also he doesn't have to use fencing along that side. And say there's 120 feet of fence to work with. Okay, so there's 120 feet, and this farmer sensibly wants to have as large of an area enclosed by that fence as possible. Okay, so that's the objective. So it's a max-min problem or an optimization problem. In this case, the way to optimize is to maximize the area. So it's very similar to the related rate problems in the sense that you just have these steps that you go through, and that's what I kind of like about them. It follows just a nice procedure, and it works out. So the first step is, what do you want to, I'll write max, what is it you want to maximize or minimize? And in this case, you want to maximize the area. So as soon as you say that, you need to start putting variables. Remember my note about we've got this power over mathematics. We don't have power over the physical world, but we do have power over the world of ideas to say let. So I'm going to say let A stand for area, and we want to maximize A. Maximize the area. And as soon as I say that, I need to somehow come up with some way to be able to express A. So let's call this X, and I could call this Y and Z, but I can do better than that. If this is X, this is X. And we'll leave this Y just for the present, and we'll do our thinking in a minute. But this is obviously X, and we'll call that Y. So area then is going to be X times Y. So that's the first thing. The second thing is, what is the constraint? What is it that keeps X and Y from being just as big as they want to be? This could go off to 50,000, and this could go to 100,000, whatever else. And obviously the constraint is that in this case we've got 120 feet of fence. So in answering that question, you're going to be coming up with some sort of an equation which relates these variables. And so this one is fairly easy to see. X plus Y need to add up to 120. So in other words, 2x plus y needs to add up to 120. Now, in fact, they can add up to anything less than 120, but if you're trying to maximize the total area, there's no reason to make this less than 120. Might as well use the entire amount. So there's the constraint. The third step is to solve for one of the variables. Okay, so notice that right here you have area as a function of two variables, and now if I can use this to get one in terms of the other, then I'll be able to get area in terms of just one variable. So here we go. I'm going to write y is equal to 120 minus 2x, and then let's see, I might as well all include this in one step, and so then A, just in terms of x now, is going to be x times y is equal to what? 120 minus 2x. Okay, so now I've got area just in terms of one variable. Okay, and the fourth step then is to differentiate and solve. And I'm just going to write that because it should be pretty evident what I mean by that. Let's think about this. A of x, if we were to draw out a of x, here's x right here. Here's a of x. Notice that when x is 0, the total area is 0, which makes sense. If you've got 120 feet of fence and you just have that fence pushed right up against the river, yeah, then you've got all 120 there. So y would be 120, x would be 0. And see that? If x is 0, y is 120. So you're using all the fence, but you're not getting any area out. So if x is 0, then you've got 0 area. On the other hand, what's the other way to get 0 area? If you were to take that fence and go 60 this way, and then turn it right back on itself and get 60 that way, that would also use up all the fence with 0 area. And notice that's what happens if y, let's see, what was the other one? The other one was when x was equal to 0. So now if y is equal to 0, yeah, if y is equal to 0, then notice that 2x is equal to 120, so x would be 60. So that's the other extreme. So those are your two extremes. That's your domain for x right there. There's no way that x could be less than 0. There's no way that x could be larger than 60 because you wouldn't have enough to come back to the river. So for those two values, the area is 0. The area enclosed is 0. And so in between those two, apparently, this is a differentiable function, nice and continuous and differentiable. So whatever it does, maybe you can figure out what it does, but whatever it does, it's doing something like that. And wherever the maximum occurs, either the max occurs, what did we say from the extreme value theorem? Either it occurs at the endpoint, or it occurs somewhere where the derivative is 0. Well, obviously, the minimums occur at the endpoints, and if there's only one critical point inside there, that's apparently got to be the place where the maximum occurs. So let's find out where the maximum is by taking the derivative and setting it equal to 0. And so we'll do that. Let's see, I'll just grab this. And so let's go ahead and take the derivative. In order to take the derivative, I'm going to say a of x is going to be 120x minus 2x squared. See that? Why did I do that? I don't have to use the product rule that way, huh? I can just go ahead and take a prime of x is equal to 120 minus 4x. There's the derivative. And by the way, this tells me if I factor this out, notice it's going to be 4 times 30 minus x. So this function, there's your critical point right there. This is your derivative. When x is greater than 30, the derivative is negative, so it's decreasing. When x is less than 30, greater than 0, this is your domain right here, then if x is in here, then the derivative is positive. So that means the function is increasing here and decreasing there. So in fact, the way this function the graph actually looks is like this. It just goes up, goes back down. It's in fact a parabola. So there's 30 right there. There's the high point. Okay? So the point is, that's where the maximum occurs. And so now let's go ahead and calculate what the area would be. What would the area be? Well, if x is equal to 30, you're going to have 30. And what would y be then? 120 minus 2 times 30 is 60, is going to be 60. And that's 1800. So there's your maximal situation. Turns out it's when y is twice the size of x. I should go down even a little farther than that yet, but but where y is twice the size of x. This is 60, and this is 30. Okay? So, a couple things. When I usually do this in class, I ask people what they guess, and typical guess is 40 by 40 by 40, because that adds up to 120. And notice if this were your rectangle in the form of a square, the total area would be 40 by 40 would be 1600. Whereas we got 60 by 30, so we got 1800. So we ended up with 200 more feet, square feet, by doing it this way rather than this way. But why is that? I mean, aren't squares and so on, aren't they typically the best, the most efficient way to, if you were to build a house or whatever else, and you only have a certain perimeter to make it a square? Isn't that typically the best way to do it? What's different about this? And the answer is that we're up against a river. So we've got two things. If it weren't for the river, then then making it a square would be the best. 30, 30, 30, 30. If you didn't have a river, you'd want to make the thing into the form of a square. But with a river, why does that make a difference? Because you're getting this for free. See that? You're getting that for free. You don't want to. You'd get even more of a side for free if you here's your river. If you made the thing like this, and you made this 118 feet, and this 1 feet and 1 feet. Now you're making a lot of use of the river. The problem is now you're not making use of the fact that a square is your best deal. So basically you want, those two things are fighting each other again. There are lots of things in mathematics where you have this tension. So you have two things in tension here. Without the river, the square is the best deal. With the river, you want to use the river as much as possible. So how do you tie those two things together? Well, the way they tie together is that basically you have half of a square. What you do is, if this were the river just in the form of a line, then it turns out that this is your rectangular area, which is just half exactly of a square. So notice, if this extended another 30 feet on this side, you'd have yourself a square. So there's all sorts of interesting mathematics just in this one simple problem. Okay? One other thing that I'm going to mention in this problem, again, is that another way to show that this is a maximum, other than just the natural fact that we knew the minimums occurred here, and so it had to be a maximum rather than a minimum or anything else, it's called the second derivative test. And the second derivative test, I don't use it all that much. Well, some people do, so I just figured I might as well mention it to you. But wherever your critical point is, so there's a critical point, a place where in particular, it's a place where the first derivative is 0. Then, if the second derivative of c, let's take the second derivative here. So here's the first derivative. What's the second derivative? Second derivative is going to be what? -4? So in particular, if you threw the value 30 in here, that's the critical point. It's no matter what you throw in there, it's going to be -4. Okay, it's -4. It's not a very good negative. Come on. That's what happens when I'm bending over. -4. Okay? So if the second derivative is less than 0, then f of c is a relative max. Why is that? If the second derivative is less than 0, what does that mean the first derivative is doing? If the second derivative is less than 0, that means the first derivative is decreasing. So by decreasing, notice what's happening to the first derivative here. It's starting at whatever, 3, 2, 1, 0, -1, -2. It's decreasing as you go. See that? The first derivative is decreasing. So if the second derivative is less than 0, that means the first derivative is decreasing, and if the first derivative is decreasing, it basically means it's concave down, and you've got yourself a relative max. Similarly, if the second derivative is at c is greater than 0, then the same sort of thing, then what happens? If the second derivative is greater than 0, then that means that what's happening to the first derivative. If the second derivative is greater than 0, that means that the first derivative is increasing. And see here, the first derivative is increasing. It's going from -4, -2, -1, 0, 1, 2, 3, 4. I'm talking about the derivative now, not the function. Okay, the derivative is increasing as we go. So the derivative is increasing, and since the derivative is increasing, you've got yourself a convex function right there, and so you've got yourself a relative minimum. F of c is a relative min. So I could have mentioned that all the way back when we did all the graphing, but I really care. I like to do graphing without that. It's not. I just don't care for it all that much. I usually use other ways to think about it rather than that. But that's, you'll see that in most every calc text. So I guess that should be part of essentials of calculus. So we'll stop there, and next time we'll do another max min problem. We've got some really nice, interesting ones to show you coming up. Okay.